Okay, this should work. So starting right about now, what we're going to talk about today, I'm going to start with this parabola, our, see how far we get, our numerical methods of integration. Numerical methods of integration. That's where I wanted that to be.
So is it completely new?
We've talked about it a little bit. It shouldn't be completely new, but we'll see. Okay, a couple of different ways you can integrate. First thing I think you have to remember is what an integral really is. An integral is always finding the area, just like an absolute value is always finding the distance from zero. So your integral is always finding the area. 9 times out of 10 in this course, you're doing that by anti-deriving, but not always, okay? So first numerical method we're going to talk about is using Riemann rectangles. So this isn't completely new, Andrew. We've talked about Riemann rectangles before. They're sort of that one indicative rectangle of what's going on. You know what I mean? Just remember, an integral is always finding the area, which means it's always multiplication. It's always a base multiplied by a height of a rectangle, and then you add up a bunch of those rectangles. Now the cool thing about an actual integral is it adds up an infinite number of infinitely thick, thin rectangles. That is so awesome. But sometimes you can't do that. This is the function y equals 4x minus x squared. We could anti-derive this and find the area between this function and the x-axis very easily. But we're not going to. Okay? We're going to do this the hard way. Take an easy function, go back and do it the hard way. We're going to make some guesses, and we're going to know those guesses are wrong. The first thing is we are going to look at is, let's see, right and left. Left-hand rectangles. Left-hand rectangles. Left endpoint rectangles, they're sometimes called. I am going to find this area with 4 rectangles. Okay, first off, taking a look at this graph. I want to divide this graph into 4 rectangles. So I'm going to divide the x interval into 4.
Should be 1.
1 each?
Or, yeah.
Chris, you're making an assumption. You're making the assumption that I'm going to want to go from 0 to 4. That I'm just going to want this region bound by the parabola and the x-axis. Guess what? You're right. Okay. But in general, and I don't have a lot of room to write today, I'll write this more clearly. In general, wait until you see the instructions say the area between the parabola and the x-axis or something like that. That could be a good trick question on the AP, is like, find the area, and you just immediately go, oh, okay, they obviously want this, and really they want something down here. Okay, so what we're going to do for these rectangles, we're going to divide this into 4, these rectangles are going to have 4 bases. That base, that base, that base, and that base. Are you all at that base? Okay, stop, we're recording. Now, we have to pick a height for these. If you're told to find a left-handed area, okay, then you have to pick the height of the rectangle based on the y value to the left. Okay, this can get a little bit weird sometimes. You don't actually want to overthink this. You just kind of want to process it. Like, okay, this is the base of a rectangle. At the left side of this rectangle, what is your y value? 0. So this first rectangle has a height of 0. If you think about that, that's kind of stupid. It's like, if it has a height of 0, it's not really a rectangle. But don't overthink this too much. If you're told to find... It's a line, I know it's a segment actually. But if you're told to find left-hand rectangles and the first one's 0, then you've got a rectangle with a height of 0. Tough. How tall is my second rectangle then? Well, I'm using this rectangle here. If I go up from the left side of the base, I hit 3 on my graph. This is a nice easy graph, it's pretty good visually. Sometimes you might have to plug 3 into your function and figure this out. It won't be as visually obvious, but yeah, this one goes up to 3. So this is my second rectangle. Any questions on where I got that one from? Okay.
What's the point of making the first triangle if it's always going to be 0?
It's not always going to be 0. It just happened. I happened to pick something that goes through the origin.
When would it be 0?
If I had made this a different parabola that, say, was over this way more. In fact, let's say I picked just y equals 4 minus x squared.
Intersection at the origin.
Yeah. And we chose to start at the origin. What if I'd said use 2 rectangles and have, find me the area from 1 to 3?
Right.
You know, then it'd be a totally different shape. So again, this is like, this is sort of where I don't want you to overthink it or look for a pattern that's not there. You can just follow this process a little bit mindlessly, honestly. If you're told to find using left side heights, left side height is 0, roll with it. Okay, here's my second base. This left-hand side is 3. My rectangle is 3 units high. Looking at my next base from 2 to 3, the left-hand side is 2, height is 4. Don't try to follow the curve, just go over 1 and draw your rectangle with your height of 4. Okay?
Because in the end, the stuff outside averages out with the stuff that's inside to the left.
You would hope, but often not. We're going to talk about that a little bit. Like when do certain things make sense. For my last base, I look at the left-hand side. I go over my height of, it's got, my left-hand side of this base has a height of 3. So I just draw my rectangle with a height of 3. And the area that I'm going to find is this area.
And that'd be the area for the problem.
This would be your, yeah, very good. This is, you have to phrase this fairly specifically, and they'll phrase it really specifically in the problem. You know, like if you, in college courses, in your textbook, a little bit on the BC exam, there's talk about finding error, like finding how off you are. And then this little non-existent area, I'm just going to indicate that that's there. You know, how far off are you? And there's a pattern to this somewhat. For example, if I'm using a left-hand rule, look at what happens on this parabola. If I'm using a left-hand rule, when the function is increasing and concave down over here, first derivative positive, second derivative negative, I know, because it's increasing and frowning. Don't forget that stuff. Okay, I lose area with a left-hand rule. When the function is decreasing and frowning, I gain area with the left-hand rule. Sometimes it'll average out nicely, Andrew. Sometimes it won't. Jordan, you had a question?
But that was I was going to say, wouldn't you just even it out?
I don't know. I think it does look like this will be pretty close to this, but not exactly, because remember, this isn't a triangle cutting across here. The fact that this thing is concave down means I'm getting a little more area here and a little less area here, and I think I'm losing a little bit more than that here. See how this bulges outward? So I think what I lose here is going to be slightly more, than what I gain here. That's just a visual guess on my part. But there are a couple of rules, like you might get a general question somewhere like, if a function is decreasing and concave down and you use a left-hand rule, will you be overestimating or underestimating area? And you might have to draw something down where to go, okay, if I'm using the left endpoints, oh yeah, I'm always getting this extra area. Okay? If it's up and concave down and you use left-hand rules, you're always going to lose some. So the volume, skipping ahead to something else. So that,
0.
yeah, the volume of that is 0. So the area here,
Imagine if they made you set up a ball for that and then it was just like, what's the line?
yeah, right. The area here is going to be 0 plus 3 plus, that's an area of 4, right? 4 times 1 plus 3 units. So notice I'm using an approximately sign. It's about 10 units. About 10 units squared. That's your area approximately. Okay? That's with left-hand rectangles.
You use right hand when it's on the left side of the y-axis.
Honestly, no, use right hand or left hand whenever they tell you to. Right? The problems on this is one of those units where, you know, your calculator I've shown you can approximate this. This is not something that most engineers do. There's one exception to that I'm hoping to have time to talk about. This is not something most people do in real life. So this tends to be, I'm kind of teaching this one towards like, do whatever the problem says. And we'll go over some examples.
What engineer uses?
I'll give you an example of where something like this can come in handy, hopefully at the end. There is one in the homework tonight. All right, so now, any questions on this that I've done here? Just geometry, draw it that way, okay. Now, let's see. Start over. Okay, now, same thing. All right, now, we're going to approximate area, Jordan, with right-hand endpoints, with right endpoints.
Same one?
Yep,
Wouldn't it be the same?
I don't know, will it? Are you sure?
No.
And 4 rectangles.
It
The
looks
other
like
thing-
it'll be the same.
Let's find out. Now, sometimes your textbook of the AP will be a jerk, and they'll give you like something from 0 to 4, and they'll say use 6 rectangles, which means you have to split this up into 6 even
Because if
things.
you slice
Try to
it,
do fractions.
because if you slice it down the middle, it'll be a mirror image, then you can assume that it's gonna be the same area.
Let's find out. What were you saying, Jordan? I was saying sometimes they'll say like split this into 6 rectangles.
Okay, so it will tell you how many rectangles it wants.
Usually, yeah. Yeah, there's one exception to that, and I'll hopefully again have a chance to go over one of those. This again, I'm going to say 4 rectangles. Andrew's pretty sure we can just assume it'll be the same. Well, let's see. If we're using right endpoints now, so I look at my base. Here's my right hand. I go up. That's at 3. Here's my 3 rectangle. I go over to 2. That's my next base.
But
That's
use
4.
right hand and left hand, you can't choose one.
Problem will sometimes say, or sometimes the problem will say prove they'll be the same. They're really pretty specific on these. There's no like general rule like if it's a related rates problem, which doesn't have area in it, but you know what I mean? There's no like if it's this type of problem, use this. If it's this, this is just the idea that you understand that an integral is area, and there are a lot of ways to do it. Also, I don't know how often this comes up, but okay. Once again, though, let's make sure you get this. Here's my 3rd base. So I go to the right-hand side. That hits it at 3. This base, it's again 0. So we once again have rectangles that are
So,
3 high,
is that
4
what
high, and 3 high. Andrew was correct. It is the same thing.
But they, in some cases, they could not be the same thing?
If it's not
yeah.
even on both sides, if it's like a weird thing that then like flattens on one side, it's like really sharp on the other.
Or, it's an even simpler case than that. What if I'd said from 0 to 5, and you had to draw a rectangle down here that was negative?
Yeah, that wouldn't work.
Then right and left hand wouldn't. What interests me is symmetry.
It's
If you're given a symmetrical area to find.
Yeah.
Then you can just assume that.
What would
I
that
can't
be,
think of an exception to that
bisymmetrical?
off the top. Pardon?
What's the symmetrical for 2? Bisymmetrical.
Yeah. Bilateral symmetry is what they usually call it. If the area you're trying to find is bilateral symmetry, oh, and Andrew, you're given an even number of rectangles.
Oh, true.
Like there's a, I mean,
Well,
the
if
problem
it's
could be a
fifth one
real
and that
germ.
one, it would still be the same. The
The 5th one would still cut it here, yeah.
Yeah.
There's probably some. Okay. Sorry. We'll recover somehow. We're professionals. All right. This area will be approximately 10. Yeah, you can figure out the patterns to it pretty easily. But any questions on how you find a left to right hand approximate area? Okay. And think about it. I'm going to let you think about it tonight in the homework a little bit. Just about. Again, look at this one though. If this thing is going up and it's concave, it's increasing, but it's concave down. Again, first derivative is positive, second derivative is negative. Right-hand endpoints definitely always gives you more area. In this case, over here where it's decreasing and frowning, right-hand rule definitely loses some area. So you have to think about that a little bit. That's a quick introduction to this. Now I'm going to go on to a new rule. Any questions on right endpoints, left endpoints? Draw your rectangles. I've seen some problems for, where they're real jerks, and it's just like, it's from 0 to 4, use 7 rectangles. And it's just, can you make the fractions?
Do the answers vary based on the amount of rectangles?
They can.
More rectangles, more active.
Very good, yeah, more rectangles, yes. I understand the question, Chris, yeah. The more rectangles you get, the smaller these little
Is,
extra
Right.
areas
is this
are.
like we're pretending
Infinite
the
rectangle.
Bravo is a triangle, or we're doing?
No, that's
like
next.
the moving the things?
No, that's next. This is just approximating with rectangles. The more rectangles you use, the more accurate you are.
Yeah,
Another use for thinking like this is one of my first assignments in an engineering class in college was to write a computer program that did this, where you put in the function, you put in the number of rectangles, and the program had to give you the numerical, the area. So you guys get the basic idea, right?
yes.
Excellent. Ike does not see the point, but he gets the basic idea. All right, now, trapezoid rule. Okay.
It's the one
Trapezoid rule. Okay, trapezoid rule. We're gonna do this one. Your instructions here are approximate the area from,
Oh, you didn't do a sign-in sheet today.
no I didn't, x equals 0, thank you, to x equals 4. Okay, approximate the area from x equals 0 to x equals 4 using trapezoid rule and 4 intervals. Trapezoid rule and 4 intervals. Okay, the trapezoid rule is a really good way to approximate this stuff. It's got its own little quirks as to when you're overestimating and when you're underestimating. But once again, I'm going to make 4 intervals. Here's 1, here's 2, here's 3, here's 4. Now the trapezoid rule sometimes looks like a triangle rule. Like, that's what you just reminded me of. But in this case, I'm going to go up to my function. And what I'm going to do is I'm going to connect the 5 endpoints with straight lines. And except for him, I'm going to attempt to connect them with straight lines. I should be in that other drawing software.
So are you more accurate with that rule?
Depends on how many trapezoids you use. If you use more trapezoids than the other, in general you will be, because look at, all we're doing is losing tiny bits of area, as opposed to those huge areas we were losing and gaining. And also it depends on the shape of your curve. A trapezoid rule in a concave down area is always going to underestimate. Trapezoid rule, if this thing were smiling,